Let us give a very quick revision to the notes of the whole syllabus, and definitely in your exam you will have the questions from these notes. So starting with the first unit, electrostatics, the first topic is of charge. Charge, it is a property of matter because of which it experiences electric or the magnetic effect. It is of two types, positive and the negative. It is a scalar quantity. Charge is a scalar quantity. And its properties, it is following the conservation of law, conservation of electric charge. Charge can neither be created nor destroyed. It remains constant. Quantization of charge. Quantization means discrete or one particular value that is allowed. It follows the formula. The formula is very important. Q is equal to plus minus Ne, where N is the integer. This N integer can be a number 0, 1, 2, 3. It can't be a fraction. It is just like there can be 2 students, 3 students. It can't be half student. So it is like that. So this is an integer, and E is the electronic charge, 1.6 into 10 power minus 19. Additivity of charges. Since these are the scalar quantities, so like numbers, you can add or subtract them. There is no need to apply the law of vector addition here. Next is the Coulomb's law. According to it, it is acting on the two stationary point charges. It can be attractive, it can be repulsive, and this force is directly proportional to the product of charges and inversely proportional to the square of distance between them. In this, when we have the constant 1 by 4 pi epsilon naught, the value is 9 into 10 power 9, and the unit is Newton meter square per coulomb square. Epsilon naught is the permittivity in the vacuum, and the value is 8.854 into 10 power minus 12, and it is the lying in the denominator, so unit get reversed coulomb square per Newton per meter square. Then is the relative permittivity. It is the ratio of epsilon medium upon epsilon naught. Epsilon medium is permittivity in the medium, and epsilon naught permittivity in the vacuum. Here we define one more thing, that is K constant. It is the ratio of the electrostatic force in the vacuum to the electrostatic force in the medium. Since this lies, if the force is inversely proportional to epsilon, so because of dividing them, they got crossed. Epsilon medium is in numerator, here force medium is in denominator. So keep this thing in mind. The next is the principle of superposition of electrostatic forces. According to it, if Q naught is any charge and it is surrounded by number of charges, then the force experienced by Q naught is due to all those charges can be added up according to the vector sum of the forces, and this is given by summation I to 1 to the n qi upon ri square. The fifth is electric field intensity. A test charge Q naught, it is experiencing an electric force F due to some source charge, say Q. It is given by F by Q naught, where the Q naught is having very small value so that it won't interfere with the field area of charge Q. It is a vector quantity, and SI unit is Newton per coulomb. Electric field due to point charge is given by just, it is the formula of the electrostatic force only, but here the force is divided by the charge, test charge. So it is not having the one of the charge within the formula. So it is E is equal to 1 by 4 pi epsilon naught Q by R square. In place of force, we are having one more Q. Electric field due to system of charges. Again, it is a superposition principle in the case of electric field. E is electric field at a point, say P, due to system, number of charges. And according to the principle of superposition, you can individually add those electric fields, and the total electric field is given by 1 by 4 pi epsilon naught summation I is equal to 1 to n qi by ri square. The next is the electrostatic force and electric field due to continuous charge distribution. I have taken the two of them together because same derivation is there. If we are considering the type of charge distribution, for the linear charge distribution, we are having the small charge element of length dl and charge having dq. Here the linear charge density lambda is equal to q by l, or lambda is also equal to dq by dl. From here we have dq is equal to lambda dl. So in place of the charge we will put lambda dl and summation for the whole length. We will get the total force. And in case of electric field, we will get that this is summation from L lambda dl by r square, the electric field experienced. Similarly, for surface charge distribution, we'll take a small area element, and again here the surface charge distribution is taken by sigma, the surface charge density, and putting this in the formula for the force, and this is for the electric field, q naught by 4 pi epsilon naught integration of surface sigma ds by r square. And in case of electric field we won't be having this q naught charge because it get divided. Volume charge distribution, volume charge density rho, and here the q will be replaced by rho dv, and summation for the whole volume we will get the total force. And in electric field again q naught is not there, but formula remains the same. Now the ninth point is about the electric lines of force. These are imaginary curves that are drawn in such a way that tangent to it at each point gives the direction of electric field at that very point. They originate at positive charge and terminate at negative charge. So they do not form closed loops. They do not exist inside the conductor. It means electric field inside a conductor is zero. They do not cross each other. In case if they cross, then at same point there will be the two directions of electric field, and that is not possible. So they do not cross each other. Electric field lines originate and terminate normally in the normal direction from surface of the conductor. So these are the properties. The next is electric dipole. Electric dipole is a system of 2-point charges. They are equal in magnitude, but their nature is opposite. One is positive, other is negative, and they are separated by a small distance, and that will form an electric dipole. The next is electric dipole moment, denoted generally by P. It is the product of the either of the charge. Dipole is having two charges, either of the charge it is taking, and distance between them. Minus q and plus q charge separated by 2l distance. So electric dipole moment is given by the product of any of the charge q and the distance between them. The direction of the electric dipole moment is from negative towards the positive in this direction. Since the direction is specified, it is a vector quantity, and the unit coulomb meter. Next is the electric field at any point on the axial line or end-on position of electric dipole is given by E axial electric field is 1 by 4 pi epsilon naught 2 pr. R is the distance at which that point is lying on the axial line, and L is the half of the distance between the two charges. If L is very less than R, then we can neglect L in comparison to R, and in that case the formula becomes 1 by 4 pi epsilon naught 2 p by r cube, and the unit is Newton per coulomb. The direction of this is same as that of the electric dipole moment, that is from negative towards the positive charge. Now the 14th point is about electric field due to any point on the equatorial line or broadband side on position or perpendicular bisector of electric dipole. It is given by 1 by 4 pi epsilon naught dipole moment divided by r square plus l square to the power 3 by 2, and again for L very less than R, this is given by 1 by 4 pi epsilon naught p by r cube. If you compare it with the electric field due to a point lying on the axial line, so this is half of that, or if we divide those two results we will get the value 2. The next is torque on electric dipole is given by tau equal to P cross E, where P is the electric dipole moment and E is the electric field. SI unit is Newton meter, and if the angle between the dipole moment and the electric field is 0 or 180 degree, the value of this torque comes out to be 0, and when it is 90 degree, it is maximum. Dipole is in stable equilibrium when the angle between the dipole moment and electric field is 0. It is in unstable equilibrium when angle between them is 180 degree. The net force on electric dipole in a uniform electric field is 0. It means if the uniform electric field is not there, if it is non-uniform, then net force is not 0, the value of force will lie. In the uniform electric field, no force is there, that is translatory, but it experiences torque. Electric flux, it is the number of electric field lines that normally pass through that surface, and this is denoted by phi, and it is equal to the dot product of electric field to the area enclosed by the surface. Since it is the dot product of two vector quantities, that is why it is a scalar quantity. The unit is Newton meter square per coulomb. And the Gauss law, the total electric flux linked with the closed surface is given by integral of the closed surface E dot ds, and it is equal to 1 by epsilon naught times the charge enclosed by the surface. The surface here considered is a closed Gaussian surface. It is an imaginary surface. Next point is of the electric field due to various kind of charge distribution. Here we have taken the types of charge distribution and the electric field associated with it. For infinite long thin straight charged wire of linear density, charge density, it is lambda. It is given by E is equal to lambda upon 2 pi epsilon naught r. Thin conducting and charged spherical shell of radius r. The radius is given by the capital R. If the point where we are studying lies inside, then E will be equal to 0 for the distance less than radius. It is equal to 1 by 4 pi epsilon naught q by r square for r equal to r when it is lying on the surface of that. Then the next surface of the spherical shell. E is also equal to epsilon by sigma by epsilon naught, where sigma is the surface charge density. Electric field is equal to 1 by 4 pi epsilon naught q by r square for r greater than, the distance is greater than the radius of the spherical shell, and it can be given by sigma r square divided by sigma over r square. R is the radius and r is the distance over which it is being observed. Here the surface charge density is given by q by 4 pi r square. Then the thin infinite plane sheet. Electric field is given by sigma by 2 epsilon naught for non-conducting plate, and for conducting plate in the denominator 2 won't be there. Electric field is equal to sigma by epsilon naught. Then the case of two equally and oppositely charged parallel plane sheets. Electric field is equal to sigma by epsilon naught between the plates, and outside the plates electric field is equal to 0. Now in the 23rd point, electric potential, it is equal to the amount of work done in bringing a unit positive charge from infinity to a point within the electric field against electrostatic force without acceleration. So it is given by work done upon charge. Since it is the ratio of two scalar quantities, it is a scalar quantity and the unit is joule per coulomb. Work done in moving a test charge from one point to other. So the difference of two potentials, that is given by the work done in bringing a charge from a point say A to B by Q naught. Electric potential due to point charge, it is given by 1 by 4 pi epsilon naught Q by R. Then the potential, this is the positive charge. Positive charge always move from higher potential to lower potential. This is the nature of the positive charge, that potential will be moving from the higher one to the lower one. On the other side, the negative charge flows from lower to higher potential. Then the electric potential due to n number of charges, again it is like superposition principle we did in force as well as in electric field. For n number of charges, the summation goes from 1 to n qi by ri. So potential is given by 1 by 4 pi epsilon naught sigma I equal to 1 to n qi by ri. Electric potential due to an electric dipole at any point whose position vector is r with respect to the midpoint of the dipole is given by 1 by 4 pi epsilon naught P, the dipole moment, cos theta over r square, where theta is the angle between r position vector and the dipole moment P. Now the 29th point, it is about the electric potential due to electric dipole at a point on axial line. That is given by 1 by 4 pi epsilon naught dipole moment divided by r square minus L square. 2L is the distance between the two charges of the dipole, and r is the distance that is lying on which the point on the axial line. If this L is very less than r, then the above relation reduces to L square can be neglected, and dipole moment by r square 1 by 4 pi epsilon naught constant is there with it. Next is the work done in rotating a dipole from, say, angle theta 1 to theta 2. The work done will be given by the product of dielectric dipole moment, electric field, and difference of the two angles for the angular rotation. The potential energy of electric dipole when it makes an angle theta with the direction of electric field, this is given by the negative of product of dipole moment and the electric field and cos of angle between them. It means it is the dot product of dipole moment and electric field. Next is the relation between the electric field and potential gradient, and that is given by the derivative of the distance with respect to the potential minus dV by dr. Then is the equipotential surface. Equipotential surface has same electrostatic potential at every point. As the word it is indicating equal. Electrostatic potential system of 2-point charges is given by the product of those charges and the distance between them. 1 by 4 pi epsilon naught is the constant. Next is the capacitor. It is a device that is used to conduct the electrostatic potential energy, and electrostatic potential energy charges acquired by it is directly proportional to the potential. And when we take out the sign of proportionality, C is the constant. C is the capacitance of the capacitor, and its SI unit is farad, denoted by capital F. Now the 36th point, it is about parallel plate capacitor. It consists of two conducting plates, each of area A at a distance small d. Then capacitance is given by, the formula for that is C is equal to epsilon naught A upon D. If the vacuum is between the plates, if that is replaced by some dielectric constant K, then in that case the epsilon naught is replaced by K epsilon naught A by D. Capacitance of a parallel plate capacitor filled with dielectric medium of dielectric constant K is given by, this is the formula, C is equal to epsilon naught A, D is the distance between the plates, and T is the thickness of the plate that is being introduced. T is the thickness of dielectric plate. So this is given by D minus T plus T divided by K dielectric constant. Capacitance of an insulated spherical conductor is given by C is equal to 4 pi epsilon naught into R. The next is the introduction of dielectric medium into the uncharged parallel plate capacitor leads to change in the physical quantities as, if we introduce the dielectric medium between the plates of the capacitor, then what changes it will make? Charge. There will not be any change in the charge. Electric field decreases as the new electric field will be the original electric field divided by the dielectric constant K, and K is always have value greater than 1. So this is the reason we will be having the decreased electric field. Or you can understand in this way, if in the formula this K will come in the denominator, then it is going to decrease. If it is coming in the numerator, it is going to increase. For example, if we are talking about the capacitance, in capacitance epsilon naught is in the numerator, So when we replace it by the dielectric medium, it will come K epsilon naught, and it is going to increase. So capacitance increases as the new capacitance will be K times the original capacitance. So you have to keep in mind, you have already learned these formulas. So only thing is to be seen whether the K is coming in the numerator or the denominator. So potential difference, it decreases, and electrostatic energy also decreases. Introduction of dielectric medium in a charged capacitor, it is connected with a battery. Now this capacitor is connected with battery, then the potential difference, there will not be any change. Capacitance increases by the same ratio Kc, charge that will also increase, and electric field, again there won't be any change. There is no change in potential difference and electric field. Capacitance and charge going to increase, and the electrostatic potential energy, that will also increase on introduction of the dielectric slab that is connected with the battery. The next is the series combination of capacitors. If capacitors are joined in series, the charge on each capacitor remains same. There are two things, charge and potential difference. So charge is going to remain the same. On the other hand, the potential difference, the number of the capacitors are joined, their potential difference will be equal to the algebraic sum of the potential difference across each capacitor. For example, if three capacitors are joined, then their potential will be given by the sum V1 plus V2 plus V3, and the equivalent capacitance for these three capacitors will be given by 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. This is the series combination. And if n number of identical capacitors are connected in series, then equivalent capacitance for that is given by the capacitance by n. So these are about the series combination of the capacitors. Now we are going to talk about the parallel combination of capacitor. It will just go reverse of the series combination. Here, in where the capacitance was same, here the potential difference across each capacitor is same. Total charge will be given by the algebraic sum of the charges on each capacitor. If suppose Q1, Q2 and Q3 are the charges on three capacitors that have been joined, so Q will be given by Q1 plus Q2 plus Q3 according to the statement. Equivalent capacitance, there in the series combination it was 1 upon C1 plus 1 upon C2 plus 1 upon C3. In the parallel combination, for three capacitors, the equivalent capacitance is given by the simply adding C1 plus C2 plus C3. The equivalent capacitance of n identical capacitors in the parallel combination is given by the product of the capacitance to n. The next is the 43rd point, is about the electrostatic energy stored in a capacitor, that is given by half CV square. Now Q is equal to CV. According to that, we can make changes in this. So that will also be equal to half QV, that is also equal to Q square upon 2C. Energy density. Energy density is energy stored per unit volume, and the value of that is half epsilon naught E square. Dielectric constant, it is the ratio of the capacitance in the dielectric medium to the ratio of the capacitance in the vacuum. So this is about the dielectric constant. The 46th point is about the loss of energy that occurs when two charged capacitors, they are connected with each other and they will share the charges till both of them acquire the common potential. Same potential will be there. In this process, there will be the loss of energy that is given by delta U, is the change in the energy that have been because of the connection of these two charged capacitors. Let C1 and C2 be their capacitances. So product of them, V1 and V2 are their potential. So V1 minus V2 whole square, that is divided by 2 C1 plus C2 in the denominator.